given language is a regular language. So again, please mind me for my crossover between regular and context-free languages. All right. The tool that we use to do that is called pumping lemma. So the pumping lemma is the tool that we use to test whether or not a given language is context-free. So let's investigate how it works. Number one, right? So it says, let L be an infinite language accepted by finite automata. So we can only test for infinite languages. So that is one of the limitations. You can only test for infinite languages, which means there is a loop that we are going to be using. We are told that it's an infinite language accepted by finite automaton with n states. So our finite automata has got n states. Then for all words in L that have got more than n letters, so what is the significance of n letters? So the significance of n letters is that if you have got n or more letters, it then means that you have looped one or more times. Right, because we say that there is a theorem that we discussed last time. We say that each and every one of the finite automata, right, if they accept a word, then they accept a word that is got the same length or less than at least one word that is got less than the number of states in terms of length or equal to the number of states. So anything more is guaranteed to have looped one of the states. And if you have a loop, then it means you can generate an infinite language. Right. So then they say, then for all words in L that have got more than n letters, right, they are strings X, Y, and Z. So we are saying that we can convert W, a word that has got more than n letters, right? So we are simply saying if length of n, length of W is greater than n, then we can convert W into these substrings, right? And these substrings will be of the format, and say we say Y is not now, right? And length of X plus length of Y are less than or equal to n. So we're saying length of X plus length of Y plus length of Y is less than or equal to n. So that is the restriction that will be facing. So in order to now deal with these restrictions, or the last restriction is that all strings of the form x, y to the power of n, z from n is equals to 1 to 3 should be in L. If we can get a word that fulfills the following elements. Number one, the length is greater than the number of states, right? Number two, we can break it down in such a way that y is not now and x and y are less than or equal to n, right? And number three, if we continuously pump y for each of those words, we increase y gradually or periodically, right? All those words are still going to be in the language, right? So if we have a word such as that, and we are saying that it belongs to a language, then we say that language is a regular language. All regular languages should behave in that manner. Right. So now, that is what pumping lemma says. So the impact of saying that the length of X and the length of Y is less than or equal to n is as follows. Right. We say that because, or the implication, let's rather say the implication. The implication of that is as follows. If the length of Y and the length of X are less than or equal to n, right, they do not exceed n. It means that Y is the one that makes it exceed n, right? It means that Y is the one that makes it exceed n, right? So those are the length restrictions that we have. Now let's see, let's look at this from a new perspective, right? Let's give this a new perspective. If we are given W is equals to X, Y, and Z, knowing that these are substrings, for this to work, we will see that the following has to be true, right? We need to find an allocation to exhaust all the possible allocations for X, all the possible allocations for Y, and all the possible allocations for Z. So out of a million possibilities, it may be true that only one allocation will end up working. So we need to be able to identify that one allocation. One way to do it is to limit, one way of doing it is to test individually what are the possible allocations for each. Right. So number one, if we are dealing with an alphabet, say of A, B, then it means all our words or all our substrings are going to contain A, B substring, right? Are going to contain either any of these letters. Right? So if they are going to contain any of these letters, then we can either have them containing A's only, or it can be B's only, or it can be now, or it can be containing AB substring. Somewhere in it, maybe we find an AB substring, or we can have a BA. So anywhere we form in the AB substring, or in the alphabet of AB, should be able to have, or is restricted to only these elements. It is restricted to only these elements. Right. Now, if we look at X, there's no restriction that it cannot be null, so X can be null, right? So X has got all these 5 restrictions. Y, however, has got an additional restriction that says this is not possible. You cannot make Y null. Z can have these 5 restrictions. So each X and Z can have these 5 restrictions, but only Y can have 4 restrictions. So if we look at it from that perspective, then we are saying we can test for Y. Say we choose to test for Y. If we test for Y and we find no possible allocation, so we're saying if we test for Y, test all possible allocations of Y, and none of them leads to this word xy to the power of n z being an element of the language, then the language is not a context-free language. So the language is not a regular language. Language is not a regular language. A regular language. But if we find even one choice that leads to all words of the nature xy to the power of nz being an element of the language, then it is going to be a regular language. So our task is simple, right? We list all the possible allocations of y. Then after that, we justify whether or not they will lead to the word x, y to the power of nz being in the language. If yes, then regular. If not, then not regular. Right. So let's look at a question. So before we look at this question, rather, let's look at language A to the power of n, B to the power of n. If we're given A is equals to that such that n is greater than or equal to 0, is this a regular language? Right. So let's see. Let's choose a word. Let's assume we've got n. Let's assume we've got n states in our finite automata. Then let's pick a word long enough, right? Choose W that is long enough. W is equal to A to the power of n, B to the power of n, where we know that A and B, or n, where n is equal to where n is the number of states. What does this do? It guarantees that the word that you have selected is greater than n. So if we're looking at n number of states, then this is going to make sure that it's greater than n. After we've selected that, then we know that there exists a weight W. There exists a weight W such that W is equals to X, Y, and Z. So if we have such a X, Y, Z, and we know that length of Y is greater than 2, is greater than N, so it's greater than 0. And then we've got length of X plus length of Y less than or equal to N, right? And all weights of weights X, Y to the power of N, Z are elements of video. So there should exist a weight like that. If such a weight exists, then we can confirm that it's a regular language. If not, it is not. So let's choose the possible allocations that we can find. Right. So we can then come and say Y has 4 possible allocations. Right. So we have got Y contains A's only. Then that's number 1. Number 2, Y contains B's only. Number 3, Y contains an AB substring. Then number 4, Y contains a BA substring. So these are the possible allocations for Y. Right. Now the next step becomes to prove whether or not any of these allocations. So we want to prove that none of these allocations lead to X, Y to the power of N, Z being an element of the language. So the language you are looking at is A to the power of N, B to the power of N. Right. So for us to prove that, we say then if Y contains A's only, then if Y contains A's only, then right, all the B's will be part of Z. Then all B's are part of Z. Right? Meaning Y will increase while Z remains constant. Increase while Z remains constant, leading to a weight not in the language. Therefore, Y cannot contain A's only. Right. So that makes sense for A. So basically we are saying if Y contains A's only, right, then the B's will belong to Z. So whatever, say for example, and you do not explain this in this example, say you've got AA, B, B. It's a word in the language, right? So if this is say X and this is Y and then this is all that is Z. If we pump Y, we are going to have AA, then we're going to have BB. Right. So after pumping, you're going to have more A's than B's, which is not a word in the language. Then let's do the next part. Right. If Y contains B's only, then X, or We have all the A's. We have all A's that remain constant, whereas Y is pumped. All right. Right. If Y is then pumped, it means we go on to say is to a word with more A's than B's. Is a word with more A's than B's. A word with more A's than B's. More A's than B's. Right. So therefore, Y cannot contain, it's more B's than A's, more B's than A's, because Y is containing B's only. More B's than A's. And therefore, Y cannot contain A's only. A's. Right. Let's look at the next part. If Y contains an AB substring, contains an AB substring, an AB substring, then if Y contains an AB substring, what is going to happen? If Y contains an AB substring, what's going to happen is, after pumping, so say we've got AA, BB. If this is Y, after pumping, you're going to have A, AB, AB, B. So we're going to have two AB substrings, which is not a word in the language. All the words in this language, you've got one AB substring. Then after pumping, the word will have more than one AB substring. So let's fix this. The word will have more than one AB substring. More than one AB substring, leading to a word not in the language. Leading to a word not in the language. Not in the language. All right. So this leads to a word that is not in. Now, therefore, Y cannot contain AB substring. AB substring. Then lastly, if Y contains a BA substring, if Y contains a BA substring, so we're going to have the same argument as above. Then after pumping, the word will have more than one BA substring. Have more than one BA substring. Leading to a word leading to a word not in the language. What do we know then? Therefore, Y cannot contain a BA substring. So now, none of the four suggested allocations lead to a word that is in the language. So we can then get a conclusion and say, since no possible allocation of y leads xy to the power of nz being an element of L or being in the language, we therefore negate our assumption, and conclude that it is not a regular language, and conclude L is not regular. Right. So that is the argument that we are going to use. So master these arguments, understand why we are doing them and where they're coming in. By doing so, we are then going to understand how, why, and why not. Right. So now let's look at a question now. Let's look at a question, sorry. If we look at a typical exam question, let's look at a typical exam question. There we go. So we're given the following in the 10-mark question in the exam. Right, we're given a language a, b to the power of 2, a to the power of n, b to the power of n plus 1. So what is going to happen is the a, b squared is going to be constant. So this part is constant. A, b squared, this is a constant part. It can never change. Right? So we cannot allocate any of these two to y. If we allocate any of these to y, then it's going to increase. What is going to change is this a to the power of n and b to the power of n plus 1. So our argument is still going to hold. Right? If y contains an AB substring, what do you think is going to happen? We have got one AB substring or two AB substrings in the word, right? If it contains an AB substring, when we pump it, we are going to end up having more than two AB substrings. If y contains a BA substring, if we pump it, it means it's going to contain more than one BA substring, which both these cases lead to a word that is not in the language. And then also we can also say if y contains b's only, right? It's either it's one of these b's or these b's. If it is this set of b's, then it means we are going to have our first three strings, right, are not going to be a set of a's, right? Because we know that here the fourth letter has to be, all the words in this language, the fourth letter has to be an A. So if y contains b's only and the b's fall on this part, then we are going to have the fourth letter not as an A but another B. So which leads to a word not in the language. As well, if it contains, if y is part of these b's, then it means this whole part belongs to x. It means this whole clump of is going to remain constant while we increase the number of b's. So best case scenario, if you pump one time, say it contains b's only, we are going to have a to the power of n, b to the power of n plus 2. So which means we cannot accept that word because we need the number of a's and the number of b's to have a difference of 1. Right? So therefore y cannot contain b's only. How about a's? If y contains a's only, right? In either case, it can either be the first a or the clump of a's. In either case, b to the power of n plus 1 is going to remain constant while whatever a's we are pumping are getting pumped. So this either results in a way that starts with more than one A or results with more A's than B's, right? Which generally is not a word in the language. And therefore, if we cannot find a possible allocation for Y that leads to a word in the language after pumping, we can therefore conclude that our language is not a regular language. Right. So if we go into the solution, because here they give us the first part of the solution, they say the solution starts by doing, we first assume the language is regular. So this is the assumption that we are negating at the end, the assumption that the language is regular. We are saying if it was regular, we're supposed to find an allocation of y leading to x, y to the power of nz being a x, y to the power of nz being an element of the language. Since we cannot find that allocation, it means that our assumption that it was regular is false. All right. Sweet. So that is how we go about resolving it. Then here they say, from this language, let's say, how many possible choices are there for y to check? So if in this language, we're only going to have 4. So the solution to this is going to be 4. Right? And then we can use this as a basis then now for attempting another question on pumping Lemma. Right. So these are the 4 cases that we're talking about, and then this is now the literature to prove why we cannot make that type of allocation. Right, sweet. So that's pumping Lemma. So under additional resources, I'm gonna start posting more and more questions there, so you can just go there and start taking a look as you start to practice. So this then makes this class the official. It makes it the official one, last class, right? Then we are going to meet again when we start with the revision classes. That will be at the beginning of May. So other than that, please feel free to contact me with any questions that you might have or any questions that you would have done, so that we are able to assist each other in this duration. So any other assignment questions you might have, your attempts, please send them to me. I'll gladly look at them. If you start looking at past papers, then go ahead, look at past papers, complete one, full one, send it to me for marking, and then we can maintain that relationship going forward. Right, enjoy the rest of your evening. From me to you, good day and have a good weekend.